about case study. The title is Application of Linear Algebra in Robotics. Okay, for MAT263. We are from CDCS 1434B. Okay, let's start to the first, which is introduction of this case study.
First of all, we are going to talk about introduction of the case study. Okay, robotics involve creating machines that can do tasks on their own or with some help using knowledge from computer science, engineering, and technology. Also, robot makes our life easier and safer in many ways, such as they build car and other products quickly and precisely in manufacturing, assist in surgeries and patient care in healthcare, explore space and dangerous places, help plant and harvest crops in algae culture, and provide service like cleaning and delivering goods. Then we are going to talk about the purpose of the study. In practice, this math concept help determine how a robot's part should move, design systems to control them precisely, combine data from different sensors for accurate information, learn from data to improve their performance, and find the best route to take.
Okay, we continue to the second purpose of this case study. Math is essential for designing and controlling robots since they contribute to help understand how they change over time using calculus, and then help them make decisions and learn from data using probability and statistics. And then they can help them navigate space using geometry. But for our video presentation, we will talk about how mathematics can help in describing their movement and position using matrix and vector by applying linear algebra. Okay, for the next we continue to the question.
The question for this case study is, in a mechanical system, there are three forces, F1, F2, and F3. These three forces are acting on a rigid body in three-dimensional space. The components of these forces along the x, y, and z axes are represented by the following system of linear equations. The first one, negative 2 F1x plus F1y minus F1z equal to 4. The second one, F2x plus 2F2y plus 3F2z equal to 13. And the last one, 3F3x plus F3z equal negative 1. Where Fx, Fy, Fz represent the x, y, and z components of the ice force respectively. Assuming that these forces are in equilibrium, determine the components of each force, F1, F2, and F3, such that the system of forces satisfies the given equations. Then, verify that the sum of the forces satisfy the given equations. Then, verify that the three sum of the forces results in a net force of 0, confirming the equilibrium condition.
So now I'm going to explain the solution for the question given. The question are in the form of quadratic equation. So there are three ways to solve the question, which is using substitution, elimination, and matrix algebra. So here in the question we will use matrix algebra. So first we need to write the system in matrix form. Ax is equal to b. So here they are. So to solve this question, we will use Gaussian elimination method. Firstly, we will form the augmented matrix. So we will get negative 2, 1, negative 1, 4, and for the second row is 1, 2, 3, and 13, and for the third row is 3, 0, 1, and negative 1. After that, we will apply row equivalent method REF to get an upper triangular form. So first, we're gonna swap our row 1 and row 2 to make the first element of the first row non-zero. So we will get 1, 2, 3 and negative 13 for the first row. And for the second row, negative 2 and negative 2, 1, negative 1 and 4. And for the third row, will remain the same. Then we will eliminate the first element of the second row by adding 2 times the first row to the second row. And we will get R2 plus 2R1 and then we will replace the R2. So we're gonna get 1, 2, 3, 13 for the first row, 0, 5, 5, 13 for the second row, and for the third row will also remain the same. And then we will eliminate the first element of the third row by subtracting 3 times the first row from the third row. So R3 minus 3R1 to replace the R3. So we will get the first row will remain the same and the second row also remain the same. So for the third row, it will be 0, negative 6, negative 8 and negative 40. And lastly, we will eliminate the second element of the third row by adding 6 over 5 times the second row to the third row. So R3 plus 6 over 5 R2 to replace the R3. And then we will get the first row will remain the same. The first and the second row will remain the same. And for the third row, it will be 0, 0, negative 2 and negative 4. And lastly, we will solve for the upper triangular system by using back substitution. From the third row, we solve for z and then we get z is equal to 2. And then we substitute z is equal to 2 into the second row to solve for y. And then we get y is equal to 4. And lastly, we substitute y is equal to 4 and z is equal to 2 into the first row to solve for x. And then we get x is equal to negative 1. To verify that the sum of the forces result in a net force of 0, we substitute x, y and z back into the original equation. All equations are satisfied confirming that the system is in equilibrium. Thus, the components of the forces F1 is equal to negative 1, 4 and 2.
Conclusion, robotics is an exciting field that combines real-life applications with math. Understanding the basic of how math is used in robotics can help you appreciate and even create these amazing machines. Whether through studying or building, exploring robotics is a journey into the future of technology.